All righty. Good morning, everyone. 8:30 in the morning is an insane time of day for me. So I'll be observing the sun. But I woke up without an alarm clock at 6:15. So body clock. Anyway, welcome to the thesis defense for Denise. She matriculated at the Ohio State University, which, as you probably know, now has a trademark on the word the, at least in certain circumstances. So I was thinking that maybe we should get together and apply for a trademark on the when applied to thesis defenses. Okay? Sound like a good idea?
Yeah, that sounds good.
Okay. So here's how we're going to do things. Denise will talk for about 45 minutes. Then we'll take questions from the audience. After those questions have been exhausted, we will dismiss the general audience. The thesis committee will be left behind for more questioning. And then after that's all concluded, hopefully there'll be some general merriment in the courtyard following. Okay? Any questions about all that? All right, so take it away, Denise.
All right, thanks for your introduction, Dave. So thank you everyone for coming to my thesis defense today on constraining Yarkovsky acceleration with thermophysical modeling. Let's begin with a few definitions. So Yarkovsky effect is simple in its conceit. Asteroids will take time to warm up or cool down. They have something known as thermal inertia, which is the resistance to changes in temperature. Because of the thermal inertia, there will be a delay between when an asteroid absorbs heat from the sun and when it releases it. And between those two events, the asteroid will rotate by some fraction. So where the asteroid releases the heat and where it absorbs the heat is different. And that creates a net force on the asteroid that causes it to push it in or out in its orbit. So this diagram shows an asteroid rotating in the prograde direction, and the arrows indicate the net force pushing the asteroid out in its orbit. If the asteroid were rotating retrograde instead, the net force would be pushing the asteroid in towards the sun. So the Yarkovsky force is mediated by photons. So you can imagine it's very tiny and hard to detect. The first detection was actually in 2003, about 100 years after it was first described in writing, with the half-kilometer near-Earth asteroid Galevka. Galevka was found to have drifted by 15 kilometers over a 12-year span, and that helped put constraints on its mass and density. Coincidentally enough, Galevka was actually named after the 3 radar facilities that studied it in 1995. And it's only because of its radar data that its orbit was well constrained enough to detect Yarkovsky, because it had 3 radar ranging apparitions between 1991 and 2003. And that helped to constrain the orbit well good enough so that we could detect Yarkovsky in it. So in order to constrain an orbit, you'll need to know all 6 Keplerian elements: the eccentricity, semimajor axis, inclination, argument of periapsis, longitude of ascending node, and the mean anomaly. We can freely transform these Keplerian elements into a Cartesian coordinate system with what are called the orbital state vectors, which represents the asteroid's position and velocity in x, y, and z. Typically, we observe asteroids from the ground, so we're limited to 2 dimensions. These are called angles-only observations, and we only get the asteroid position velocity in x and y. Eventually, these 2 dimensions are enough to constrain an asteroid's orbit, but you will need several decades of astrometry, depending on your precision. With radar, you get immediate access to the z dimension, so you can constrain an orbit very, very quickly when combined with the angles-only observations. There are a few major limitations with radar, however, because you'll need to know where to point your radar in to begin with. So that means the asteroid's orbit has to be well constrained, fairly well constrained to begin with. And the signal also drops by the distance squared. But since you're sending and receiving a signal back, it's actually falling by distance squared twice. So it's effectively distance to the 4th power. So you're limited to targets that are both close by and fairly large in apparent size. So we end up with hundreds more radar observations for near-Earth asteroids than we do for main belt asteroids. And for the latter case, it's only limited to the largest of asteroids, where the Yarkovsky effect is negligible. So for the past 20 years, we've seen hundreds of Yarkovsky detections in near-Earth asteroids, but none in main belt asteroids. But the theory points to Yarkovsky being present in the main belt, because near-Earth asteroids only last for a few million years on average, as they either get lost through impact events or by ejection via a close encounter with Jupiter. That means there must be a continuous source of near-Earth asteroids to explain the observed population we see today. So near-Earth asteroids and other interplanet crossers have been traced back to residences in the main belt, but then the question arises how these asteroids reach these residences to begin with. Collisions are far too rare to serve as a valid explanation, but numerical studies have shown that Yarkovsky can make the numbers all line up with it as the main mechanism. We also see an observed preponderance of retrograde spins among near-Earth asteroids, and that would be consistent with main belt asteroids spiraling in towards the Nu-6 resonance that lines the inner edge of the main belt. So the difficulties in detecting Yarkovsky in the main belt all effectively stem from the increased distance from the sun. Yarkovsky is going to be weaker farther away from the sun, and we also have the lack of radar as an issue, but there's also a selection bias going on. So Yarkovsky is stronger for smaller asteroids thanks to the more favorable area to mass ratio, and it's also stronger for low albedo asteroids because those absorb more solar radiation than they release or than they reflect. But most of our observations of asteroids are done at visible wavelengths, which makes it very difficult to find small dark asteroids in the main belt, which means our known population of main belt asteroids is full of large asteroids where the Yarkovsky effect is negligible. But even if the Yarkovsky effect was the same between a near-Earth asteroid and a main belt asteroid, it'd still be harder to detect Yarkovsky in a main belt asteroid because of the smaller angle the orbital drift would subtend. 15 kilometers at 1 AU is much easier to see than 15 kilometers at 3 AU. So we know that Yarkovsky must be present in the main belt, but there's too many asteroids to try to find the detection by chance. But if we can identify which asteroids would have the biggest Yarkovsky acceleration, then we have an easier time trying to confirm any detection by observations. So we can obtain the physical parameters relative to Yarkovsky with what's called thermophysical modeling, which represents an asteroid surface temperature distribution, or which fully models an asteroid temperature distribution and compares it with observations, where the asteroid shape is represented as a mesh of triangular facets, and each facet the thermal emission is calculated for. Originally, these thermophysical models were made to model thermal observations of the lunar surface, and they were later adapted for general planetary bodies in 1989. And all of the most commonly used thermophysical models today for asteroids are all variations of that 1989 implementation. In order to use a thermophysical model, we need both thermal data and a shape model for the asteroid. For the thermal data, I use data from the Wide Field Infrared Survey Explorer, or WISE, but we only use the 8-month period where of the first 8 months of its operation in 2010, where both the W3 band at 12 microns and a W4 band at 22 microns were available, as these bands are best for trying to constrain the expected peak of the asteroid thermal emission. We don't use the W1 and W2 band, even though there's many more years of data with those bands, for two main reasons. These only see the tail end of the asteroid's thermal emission, so they're not very good for constraining the emission, and also that they'll contain some significant fraction of reflected sunlight. And that reflected sunlight component will actually differ between W1 and W2, and also between asteroids. So it'd be very difficult to model in the thermophysical model. For the shape models, I take shape models from the public database of asteroid models from Inversion Techniques, or DAMIT. These, as the name suggests, basically take light curve data and derive shape models from them. And there are a few thousand asteroids with shape models available, but the quality will vary drastically. With a good shape model, you ideally want lots of dense in time light curves that cover the full rotation phase together. But many asteroids only have sparse data available. That means the shape models produced from that data are crude and very physically impossible, as they have large flat planes that meet together at sharp edges. So here I have an example of 4 light curves, which is out of a total of 101 for this asteroid, and that produces the middle shape model here. If you have more photometry, you get something like the top model, and you get less, something like the bottom model. You can see how when we lose more photometry, how quickly we can degrade the model. But there's also another issue of pole ambiguity. So with a single light curve, it's very hard to tell which way an asteroid is rotating. So what happens is you get mirrored solutions equally likely, one for the prograde direction and one for the retrograde direction. And that means that there are oftentimes 2 shape models for one asteroid. So we also derive some of our own shape models by adding the WISE photometry into the existing light curve data sets, and then running the inversion ourselves. So we use the same thermal data as we do for the thermophysical model, but now we also use the W1 and W2 bands, as we don't care about the thermal distinction here. The inversion treats all light curves as optical. There might be an issue with treating a thermal light curve as optical because of the thermal inertia. That means there will be a phase offset between the thermal light curve and the optical light curve, and that could complicate how the period is determined. But we note that all the WISE data is very sparse, and that you can't determine a unique period from sparse data alone. Plus, the additional constraints on the asteroid's rotation state and shape should make up for the challenges with the period. In any case, we also adopt a conservative approach to this revised model step, as we don't expect them to drastically differ from the original shape model, since all we're adding is sparse data. So we set a condition where we only accept a revised shape model with a period that's within 0.1% of the original shape model's period. It is possible that the original shape models had their periods incorrectly determined, but since we're not adding dense photometry, it's going to be hard to argue what we found is the more likely correct period. So in total, we had around 2,500 asteroids to model in our thermophysical model, but that's actually mostly limited by the number of shape models available. If we look at the WISE data alone, we had nearly 100,000 asteroids with sufficient WISE thermal data for our purposes, and we only are limited by this number because of which asteroids have shape models available. We didn't make any selection cuts on the orbital class, so the majority of our sample ended up being main belt asteroids, plus a few Apollo type near-Earth asteroids and Mars crossers. So the thermophysical model generates a thermal light curve based on the choice of physical parameters for the thermal inertia, diameter, albedo, and surface roughness. And it compares the thermal light curve it generates with observations to calculate a chi-square. We run the thermophysical model over a grid of values for each parameter to try and find a chi-square minimum. And we do this for each shape model an asteroid has. Note that the thermophysical model does not directly account for any shape uncertainties. It only calculates the chi-square based on the thermal flux values. So even a small chi-square value may not necessarily mean a good fit. So here I show 2 examples of my thermophysical modeling fits with panels for the thermal inertia, diameter, and albedo. Each of these have 10 curves, one for each surface roughness. And those are given by the combination of the crater opening angle and crater density, which combined describe a macroscopic roughness. It's important to note that the thermal inertia, albedo, and surface roughness can all vary across an asteroid surface, but with this model, we can only really calculate an average value. So we run the thermophysical model on 10 loops, one for each surface roughness, and for each one, we start from high to low thermal inertia, beginning with an arbitrary value for albedo. From those, the thermophysical model produces a diameter and a chi-square value. And from the diameter, we can get a more realistic value for the albedo on the next step of the loop, using the relation diameter has with the geometric albedo, which is PB, represented by PB here, and H is the absolute magnitude, where the geometric albedo is related to the bond albedo by some function related to the asteroid slope parameter. So the dashed horizontal line represents our 1 sigma uncertainty boundary, which is a function of the number of degrees of freedom multiplied by the minimum chi-square. Note that our estimation for surface roughness is very crude, which means that we can't necessarily believe that the single best fit curve is also the best fit surface roughness. So we end up defining what's the whole contiguous region intersected by the horizontal line for all curves and take that as our 1 sigma uncertainties. So if there is no clear minimum in a thermophysical modeling fit, we can't constrain parameters. Here is an example of such a case. So here we see that the chi-square minimum is fairly small, around 2.5, but that describes almost the entire curve. So the thermal inertia here is completely unconstrained. There's 2 main ways this can happen, even with a robust shape model. So first of all, if the asteroid is a slow rotator, that means the points of the maximum thermal absorption and thermal emission will be close together, and the thermal signal will be harder to distinguish. Secondly, if we're seeing the asteroid from pole on, that means that the thermal light curve will remain flat overall over the entire rotation phase. And then it will again be hard to distinguish any chi-square minimum. Note that we only use thermal data from WISE over an 8-month span. That means most asteroids were only observed at 1 epoch, which means we only have access to 1 viewing geometry in majority of cases. So to quantify what a clear minimum is, we look at the ratio of the maximum and minimum chi-square in the parameter space we search. And we choose a cutoff of a ratio of at least 20 to define a clear minimum, as it seemed to go well with the more common standard of chi-square under 10 cut. This is somewhat arbitrary. This is somewhat arbitrarily defined. So the chi-square cuts remove about a quarter of all of the asteroids we model. And the plot here shows only a single shape model per asteroid, but note that it's possible for multiple shape models for the same asteroid to pass our chi-square cuts, and those are included in our full results. And here we only show 1 for each. In many cases, we do end up using our revised shape model as the better shape model, but the majority of cases are still using the original DAMIT models. So one of the big hurdles in thermophysical modeling is the lack of benchmark tests to verify the accuracy of the derived parameters. We can, however, get independent checks on the diameter and albedos with techniques like resolved imaging, polarimetry, or occultation, but all these have been traditionally limited in their application or sample sizes. More available are other thermal studies with what are called simple thermal models, which assume a sphere for the asteroid shape. These can't derive the thermal inertia, but they can get the diameter and albedos for many asteroids over a short period of time. So many of the WISE asteroids we have in our sample were also had their diameters and albedos derived with the near Earth asteroid thermal model, or NEAs. And we can compare our diameters and albedos with what those were derived with. So in this plot, we showed darker and lighter regions are the 10 and 20% agreement for diameter, and for albedo, it's instead 20 and 40%. And we see that we generally have good agreement, except for these points in blue, which have one thing in common, is that they have some percentage of saturated pixels in the W3 band, which means that their thermal flux was actually lower than they should have been. This isn't as much of an issue for the WISE NEAs numbers, as they also model the W2 band, which we do not give ourselves access to. So we also see that the albedo has a larger spread compared to diameter, but this is also expected given that albedo is proportional to the diameter squared, and is also dependent on the absolute magnitude and slope parameters, which typically do not have reported uncertainties. So for the thermal inertia, we can't really compare this with anything other than other thermophysical modeling studies. And many of our asteroids do not have a pre-existing thermal inertia estimate. But we can set our expectations by looking at what the thermal inertias are for common materials. And here I show the thermal conductivity kappa, the density rho, the specific heat capacity C, and the thermal inertia gamma, which is the product of the three other parameters taken with the square root. We can see that the metals like nickel and iron have extremely high thermal inertia, but even if an asteroid was fully metallic, we would expect that the asteroid would have lower thermal inertia because asteroid surfaces are somewhat porous, and that would bring down the thermal conductivity and thus also the thermal inertia. We can see this in action with the lunar regolith. So we expect the lunar surface to be made of some kind of material like rocky soil, but the thermal conductivity is much lower. And in turn, that makes the thermal inertia something more like styrofoam than anything else. So with that in mind, let's look at the ranges of thermal inertia we have derived. So here I showed the revised models in blue and the original DAMIT models in gray. Note that many of the thermal inertias we derive have very large uncertainties and that the lower bound is frequently unconstrained. We also see several thermal inertia that are much higher than solid rock, and these are unlikely to be real because of that. What's likely happening is that the shape models being used are pretty low quality, and that introduces inaccuracy into the thermophysical model that we do not catch in a chi-square cuts because the chi-square is only directly accounting for the uncertainties in the thermal fluxes, not the shape. So we need some kind of metric to separate out these worse shape models from our fits. So we know that shape models improve with more dense light curves, but then there's the matter of defining what a dense light curve means. So ideally, you want a light curve that covers a decent fraction of the rotation phase without large gaps in coverage. What I ended up deciding on is defining a dense light curve as having three conditions: at least 30 data points that span at least 20% of the rotation phase, and the mean separation between those data points can't be more than 2%. With that condition, if we plot the number of dense light curves versus our thermal inertia, we see that at cutting things at least one dense light curve, we remove all their super high thermal inertia values from our data. We still have a few somewhat high thermal inertia points left, but these also have fairly large uncertainty, so they're not as big as of a concern. We can further compare our thermal inertia with the literature. So here I've plotted my fits in blue and red, and the literature main belt asteroid thermal inertias are in gray. So thermal inertia values in the few hundreds range has been more commonly found for near-Earth asteroids, like the one point we have at the bottom here, but they would be very unusual for main belt asteroids. We do see a few points in the literature that overlap with the uncertainty ranges of our main belt asteroids, but they all have very large uncertainty. So it's more likely that these true thermal inertia fall on the lower end of the uncertainties we found. We can also look at the trends that thermal inertia has with other parameters. There's a well-known inverse correlation between the diameter and the thermal inertia, which we can recover when we limit our sample down to only the most reliable thermophysical modeling fits. That means no W3 saturation and at least one light curve for the shape model, or at least one dense light curve for the shape model. It's important to look at the normalized thermal inertia here because the thermal conductivity actually depends on temperature, and that in turn means that the inertia will depend on heliocentric distance. So here we scale everything to a distance of 1 AU. So the normalization may be less accurate for the asteroids with more eccentric orbits, since those will change their heliocentric distance around their orbits. But main belt asteroids typically have their eccentricities topping out at around 0.35. So it's likely less of a concern here, and also that our uncertainties on thermal inertia are likely large enough to encompass such a variation. We see generally good agreement with the 500 other literature points, but we note that we don't really have many points on the small or large end to help constrain our fit. So the relationship with rotation period is also interesting to explore. It was actually hypothesized a few years ago that slower rotators should present higher thermal inertia on average, because the thermal observation will be able to penetrate deeper into the asteroid surface and reach the denser material further below. More recent studies, however, haven't been able to find a trend between these two parameters, but they were limited to sample sizes of less than a couple dozen asteroids. So here we fit our data with both a linear and a constant relation, and we find pretty similar goodness of fit values for both lines. There does seem to be a slight incline with the linear fit, but it's hard to argue that this is indicative of higher thermal inertia with rotation period for three main things. We see large uncertainties in thermal inertia as before. We have a large scatter in the data points, and we also have very few rotators above around rotation periods of 30 hours. So it makes the fit overall very tenuous. So to recap, we started with around 100,000 WISE thermal data for 100,000 asteroids with sufficient WISE thermal data, but we were limited on a number of shape models. Then we threw out about a quarter of the asteroids with the chi-square cuts, and those removes about a similar number of fits, but combined we got around 1,800 fits. And then when we remove the W3 saturation, we actually keep most of the asteroids we model, but imposing the dense light curve cut is a much stricter criteria. As combined, we end up with just under 200 asteroids for our most reliable fits. Even so, there were currently around 500 thermal inertia estimates in the literature, and of our most reliable fits, we had 150 without every previously reported thermal inertia, increasing the number of thermal inertia in the literature by a pretty sizable amount. Okay, so now that we have our derived parameters in hand, we can get their Yarkovsky accelerations. So here I showed the transverse non-gravitational acceleration parameter A2 as a function of the diameter, bond albedo, and obliquity. And we can see that the A2 is maximized at smaller asteroids, darker asteroids, and asteroids where their poles are perpendicular to orbital planes. The relationship with thermal inertia, however, is a bit more complex. So in order to have the Yarkovsky effect happen at all, you need to have some thermal inertia. As without any thermal inertia, there isn't a delay between when the asteroid absorbs and releases the heat from the sun. So the asteroid surface temperature distribution becomes symmetrical. However, if the asteroid's thermal inertia is too high, then the asteroid never releases any heat. And again, the asteroid has a symmetrical temperature distribution. That means that Yarkovsky has to be maximized somewhere in the middle of these two extremes. So when we estimate the uncertainty on our Yarkovsky predictions, we use whatever thermal inertia in our 1 sigma range that minimizes or maximizes Yarkovsky acceleration. Yarkovsky is also going to be stronger for lower density asteroids, but the thermophysical model does not constrain the density of asteroids at all. So what we do is look at the existing density estimates, but very few asteroids actually have existing density estimates, but we can instead look at the taxonomic class and the averages for each one. So using the taxonomy as a proxy, if the taxonomy is known, we can simply take the average for its class, but if the taxonomy is unknown, as is also common for a majority of asteroids, then we simply assume an S-type or C-type based on the albedo of the asteroid and use the average density for that class. Oh, also we don't assume any uncertainties on the density here, but they fall over a relatively small range in values, and they're likely going to be smaller than the uncertainty ranges in all of our other derived parameters. Okay, so with that, we can get an Yarkovsky estimate for every asteroid in our thermophysical modeling sample. If we take the smallest A2 value that's ever been reported, as our threshold, we see that we have 55 or 57 candidates up with a Yarkovsky acceleration bigger than this threshold. These include the 2 near-Earth asteroids in our sample, Toro and Cerberus, which have had a previously reported Yarkovsky detections. However, only 5 of our 57 asteroids have a dense light curve associated with their fits, and also 11 of the 57 have completely unconstrained lower bounds, as we were not able to find a lower bound on the inertia, which means the Yarkovsky acceleration is similarly unconstrained. So we wanted to try to confirm the Yarkovsky candidates we found. So we got 6 nights on the 80-inch taken between 2021 and 2022, where we observed a total of 135 unique main belt asteroids, as well as the 2 near-Earth asteroids from before, Toro and Cerberus. We tried to prioritize what were the best candidates on our list, but on any given night, we were going to be restricted to what was available to observe. So we found average astrometric uncertainties of 0.03 arc seconds in right ascension and declination, which in total range between 0.01 to 0.36 arc seconds. Note that these are effectively lower limits, as there will be unmodeled sources of errors like the tracking consistency of the telescope. But these are likely to be at a minimum here because our main belt asteroids were both bright and moving slowly. So we could take short exposures and keep the reference stars as point sources rather than trails. So ideally, we wanted to observe each target on at least 2 different nights to try to confirm any Yarkovsky, but the weather and scheduling issues precluded such conditions for most of our asteroids. So many of them end up with only having 1 night of observations. Our orbit solutions are handled through the software package called ORBIT, which includes consideration for non-gravitational effects like the relativity and Yarkovsky. In addition to our own observations with the 8-inch, we take existing observations from a minor planet center. And the accuracy of an orbit will depend on the accuracy of the observations, but for the minor planet center, the astrometric uncertainties are unavailable in most cases. So that means that ORFIT must make assumptions on the accuracy of each observations using what's known as a weighting scheme. And weighting scheme is based on a statistical analysis of past astrometric errors of other observations, which can be further separated out into variables like the historical accuracy of the site, the magnitude of the target, and the epoch of observation. So in addition to the 8 major planets, Earth's moon, and the sun, ORFIT can accommodate 17 additional perturbers, for which we use the 17 highest mass main belt asteroids. The 2 highest mass asteroids here are Ceres and Vesta, and these have the most accurate masses because they were visited by the Dawn spacecraft mission. But other masses are typically known much more poorly, and very few asteroids have mass estimates known at all. They only number in a few hundreds or so. This means our dynamic model may be missing significant perturbers. However, the gravitational force will scale much more strongly with distance than it does with mass. And the choice of any one perturber shouldn't matter outside of close encounter events, which would show up in the orbit fit residuals. So we use the 17 highest mass asteroids as our simplest case, and we can investigate further to find any possible signs of Yarkovsky. So when we run all of our observed asteroids through ORFIT, we find that we recovered the Yarkovsky detection for our 2 near-Earth asteroids in agreement with both previously reported measurement and our own predictions. But we don't find any plausible detections among our main belt asteroids. So left is a comparison of the predicted A2 values with the values we find with ORFIT. And on the right, we have the ORFIT A2 values expressed as both signal to noise and the indicator parameter S, which is the ratio of the value found divided by the expected value. So a possible Yarkovsky detection should have both a signal noise greater than 3 and an S value less than 2. S values less than 1 are valid because it only is indicative that the Yarkovsky was overestimated in some way, probably because one of its parameters was misestimated in some kind of fashion. But if the S value is much greater than 1, then the force is far too strong to be explained by Yarkovsky. So what could be going on is a stronger force in play, like outgassing. But what is more likely happening here is that there's bad observations corrupting our fits. We can take our highest signal noise point here as an example. So our highest signal noise fit is for the main belt asteroid Kristen. And that indicates there may be a problem in these observations. So if we look at the observations, we find one clear outlier at the 1994, which is a single observation with a residual of 25 arc seconds. If we remove this single observation and rerun ORFIT, we actually drop the A2 signal noise from 5.8 to 1.4. The uncertainty on A2 doesn't actually change all that much between these two runs. It's that the value of A2 shifts by that amount that drops the signal to noise. So even with this 1 point removed, it's a good idea to look at the other early observations. We see that the discovery observation is separated by over 20 years from the next group of observations at 1981. And all of these observations are biased in the same direction, right ascension and declination, which implies that they should be downweighted in some form. So ideally, every asteroid should be re-inspected like this, but it's a time-consuming process, and the manual re-rating is going to be very case by case. So it's usually only carried out when we have possible Yarkovsky detections. But since we don't have any, the re-weighting process wouldn't meaningfully change our results. So it's still worth doing to explain away all the high signal to noise cases we showed before. So we didn't find any Yarkovsky detections in our main belt asteroids, but we can investigate what would have been needed to make detection possible. In ORFIT, we can generate a set of predicted positions, assuming an a priori A2 value. From those, we can generate synthetic observations and see if we can recover the A2 signal. So here I decided to pick three main belt asteroids from our observed sample, each from the inner, central, and outer main belt asteroids to serve as our test cases. For each of these asteroids, I limited myself to the low eccentricity asteroids in order to minimize the potential of the Yarkovsky accelerations changing over the orbit of the asteroid as the heliocentric distance changes. So with the synthetic observations, I assume an astrometric uncertainty of 0.1 arc seconds, which is slightly conservative to what we found with our own UDH 88-inch observations. We also use a fixed cadence of 50 days, which may not be realistic because the asteroid will go behind the sun at certain points, making observation impossible. But this is just a simple exercise of ensuring that we have a regular observing pattern. And all that matters is that the cadence should be short compared to the total arc length. For the arc length, we vary this between 10 and 200 years in 10-year steps. And we should note that the parameter space here that we could have explored is enormous. We could also vary the astrometric uncertainty and the cadence, and also look at things like where on Earth we're observing the asteroid from. But we wanted to keep things simple to find a relation between three main parameters, so the semimajor axis, the arc length, and the detectability of Yarkovsky. Okay, so with our synthetic observations, we have a grid of points with the A2 uncertainty as a function of both the arc length L and the semimajor axis A. For a valid detection, we want a signal noise of at least 3. That means the A2 uncertainty must be 1/3 the value of the target A2. So with the semimajor axis fix on the left, we see that the arc length and A2 uncertainty follow a power law relation, while with the arc length fix, the semimajor axis and A2 uncertainty resemble more of an exponential function. So with that in mind, we can think of the combined functional form as something like this we show here, where K, C, and alpha are all fitting coefficients, which we find by minimizing the residuals using a numerical method. So with the functional form in hand, we can estimate a minimum arc length needed to detect Yarkovsky for our observed sample using the uncertainty ranges we have on our predicted A2 values and compare it with the existing arc lengths. Here we see that in every case, the existing arc length is far too short to get to the minimum threshold for detectability. And this is under ideal conditions with modern astrometry and a regular cadence. But we know that the historical data is lacking because there's large gaps and large residuals that make existing arcs effectively much shorter than they appear to be. And there's also going to be a clear difference with what's possible with modern day technology. So the historical astrometry is limited by what was available for the instruments and star catalogs. It is possible to improve these old observations with remeasuring them against modern star catalogs. And it was actually done before for 1953 observations of a near-Earth asteroid to confirm its Yarkovsky detection. This isn't always feasible, however, because before CCDs, most of these observations were taken with photographic plates, which can't be stored electronically. So to remeasure these plates, we would have to digitize them first, which can be a costly process and is also predicated on plates being preserved and stored in some fashion over many, many decades. It's hard to justify going through all this effort without any signs of possible Yarkovsky to begin with, and it does nothing to address the large existing gaps in the data. Okay, but instead we can consider the undiscovered main belt asteroids. When most of the physical parameters are unknown, the A2 is estimated from scaling the diameter with a reliable Yarkovsky detection. And currently the most reliable Yarkovsky detection belongs to the near-Earth asteroid Bennu, which was visited by OSIRIS-REx between 2018 and 2020. And thus, because of the spacecraft telemetry, its Yarkovsky measurement is known to less than 0.1% in precision. Bennu, however, is an NEA, and that means it might not necessarily be representative of main belt asteroids that we're looking for. And among near-Earth asteroids, Bennu is also notable for its low bulk density and extreme obliquity, which would also maximize Yarkovsky. So we look at our relation compared with all the thermophysical model sample main belt asteroids we see that the relation is consistently high. But if we add an additional factor of scaling everything down by a third, everything falls much more in line. So this is a very crude correction factor, but we're only looking for rough estimates, not exact numbers. So here I have the 2D function from before, now represented as an intensity plot with the A2 uncertainty as a function of the semimajor axis and the arc length. And here we see for the longest arc length and closest distance, the A2 uncertainty is at its smallest, and that drops as we go further away from the sun or observe for shorter arcs. Overplotted are the contours of the detectability thresholds for a 0.1 kilometer main belt asteroid, as well as 0.5, 1 kilometer, and 5 kilometers. So we see that for the smaller asteroids, the change in semimajor axis actually doesn't change the detectability all that much. And 0.1 kilometers is the size that the LSST survey that's expected to go up in 2024 is expected to reach in the main belt, getting down to around 24 magnitude in the R band. So assuming that these small asteroids are discovered and that they receive regular follow-up, we should be able to see Yarkovsky in the main belt within a few decades. So we can't see Yarkovsky in the main belt yet, but in a sense, Yarkovsky detections are inevitable. So for current main belt asteroids, this may take longer than our lifetimes, but the arc lengths are always going to be increasing with surveys scanning the entire sky like on a regular basis. There's also a new potential to get even smaller main belt asteroids with upcoming bigger surveys and potentially better Yarkovsky candidates to chase after. Once we have a Yarkovsky detection in hand, we can get better constraints on the physical parameters, especially when combined with thermophysical modeling to get constraints on both their masses and bulk densities and better understand one of the largest groups or to better understand the largest body of asteroids in the solar system. All right, so there's lots of people I would like to thank for this work and that I could not have done without. So in addition to my advisory committee, I would like to thank my collaborators, Joseph Hanus on the thermophysical modeling side, as well as Davide Fernocchio and Federico Espoto on the Yarkovsky and orbit determination work. My work would also not have been possible if the various third-party software generously made public or available to the community. These are being the Marco Double thermophysical modeling code, the light curve immersion codes, and the orbit distribution. I'd also like to thank my research home away from home with Roy, Brian, and Orels and C3VO teams, who somehow convinced me to work on 3 extragalactic papers while also working on my thesis, but also made my grad school studies more diverse and fulfilling. I'd also like to thank the UH88 NEO follow-up group, both in the past and somewhat more recent past, for making observing slightly less crazy every month. I'd also like to thank Luke McKay for this, for his tireless help with running the 80-inch all these years. Finally, I'd like to thank the IFA Ohana, the faculty, staff, and grads, as well as my friends and family, both online and on island, for their continuous support and making my environment the best it could be. That's all I have today. Thank you for listening, and I can take questions now.
Oh, okay, that's nice. They don't get the recognition they deserve. The day crew folks that keep the whole thing running. Everybody else there's scientists, you know, they do the observations, but you need people to keep the facility running. So it's really nice that you mentioned Luke there. Okay, questions from the audience.
I have tried to promote various people to be panelists. Unless they accept it, you know, it will be hard for them to speak. So you have been intentionally promoted to panelists so that you can participate. You should accept that invitation.
Who has control over that? Do you?
I think Raja does.
I think he does.
Yeah.
He does? Well, yeah, that's fine.
So people are promoted and they can unmute as they choose. I think it's the idea. It's Connor.
So you mentioned that for your thermophysical models, some of your sources had more than one model that passed the your chi-square test. How do you decide which model to use? You don't necessarily that all work.
So I end up reporting every model that I had that meet both chi-square cuts. So they're in the full table results, but for the A2 like plot, I just choose the best point to plot there. But usually the A2 uncertainty doesn't really change that significantly between the two fits, because usually the thermophysical or thermal inertia doesn't, like the diameter and albedo are pretty robust, but then the thermal inertia just changes a little bit.
Right.
So from your last slide, and looking at the data as it's changed with time with the number of CCD observations, how do current sky surveys and things like Rubin, where you have a big telescope, impact your ability to do this in terms of reducing the arc length that you need and making it feasible to do these on sort in the next decade or two?
For existing surveys, I don't think you'll get. So currently, most of the main asteroids are like effectively limited to arcs beginning in the 1990s, because the data before then are kind of crappy. And most of the existing main asteroids are in the like 5 kilometer range. So you're not getting those within the next few decades unless the astrometric uncertainties improve by a lot. So you're really hoping for like new smaller asteroids to be discovered, but the current surveys aren't going to be able to reach those deep magnitudes to find these small asteroids. So you're going to need basically bigger telescopes.
More questions from the audience? Questions from Zoom land? Not hearing anything. Okay, well, in that case, why don't we give Denise another hand? We can dismiss the general audience now, and this is